Today we are going to study the new chapter Complex Numbers and Quadratic Equations. The term complex numbers doesn't mean that the numbers are complex in nature. Just like the real numbers, they are another set of numbers. In this section, we are going to see what are complex numbers and why do we need complex numbers. Consider an equation x square plus 1 equal to 0. You know that the solution of this equation is x equals square root of minus 1, which is clearly a non-real number because the square root of negative real numbers does not exist or imaginary numbers under our consideration. Now you realize it is inadequate to use the real number system R to find the solution of such equations. Thus, we extend the system of real numbers to another one called as the complex number system that allows square root of negative real numbers. Now we can see the definition of complex number. Numbers which can be written in the form a plus ib, where a and b are real numbers, are called complex numbers. Here, the symbol I is called iota. Euler was the first mathematician who introduced the symbol I, read as iota, with the property that I equals square root of minus 1. Complex numbers are generally denoted by Z. So, Z equals A plus IB. Now, we can discuss complex numbers. I am going to give the definition of complex numbers again. Complex numbers are numbers of the form complex numbers. Numbers of the form a plus ib. Numbers of the form a plus ib, where a plus ib when writing, you try to remember two parts are there with. One is called, this part A is called the real part, denoted as real part like this. And B is called the imaginary part. Usually complex numbers are denoted by the letter Z. So, if Z equals A plus IB, then real part of Z represented like this. Real part of Z equal to, which is the real part, A alone. And imaginary part is the part which comes along with the number I or iota. So, imaginary part of Z equal to B. For example, if Z equals 6 plus 3I, then what is the real part of Z? Real part of Z equal to 6 and imaginary part of Z equals the number which comes along with the I, that is 3. Complex numbers can be divided into three types. Complex numbers can be divided into 3 types. The first type is that when the value of a equal to 0. You know that the complex number is usually represented with Z equals a plus ib. When a equal to 0, what happens to that complex number? Then Z becomes equal to, a becomes equal to 0, Z becomes equal to 0 plus ib, which is equal to ib. ib is a number which is purely imaginary. This is purely imaginary. No real part, so purely imaginary. Remember this condition. When a equal to 0, the number becomes purely imaginary. Consider the second case. When b equal to 0. What happens when b becomes equal to 0? When b equal to 0, the given complex number z becomes z equals a plus I into 0. I into 0 becomes 0. So z equals a. Z equal to a is purely real. This is purely real. Purely real. And come with the last case. Last case is the original number itself when both a and b both are not equal to 0. When a not equal to 0, b not equal to 0. When both are not equal to 0, the given complex number z becomes equal to a plus ib, which we can call as an imaginary number. This is called as an imaginary number. So remember these three cases for the division of a complex number. Z equal to a plus ib is the usual representation. When a becomes equal to 0, it is purely imaginary. When b equal to 0, it becomes purely real. When both are non-zero, the number is called as an imaginary number. About iota. Iota is usually represented with the I. Euler was the first mathematician who introduced the iota with the property that, remember, when x square plus 1 equal to 0, you know that x square equals minus 1, which implies x equals square root of minus 1. This square root of minus 1 can be called as I or iota. Remember, I equal to iota, I equal to the value of I equal to square root of minus 1, or it implies that what happens when squaring? I square equal to minus 1 the whole square is root of minus 1 the whole square. Root of minus 1 the whole square. Squaring both sides. So that what happens to I square? I square equal to the root get rid of and it becomes minus 1. I square equal to minus 1. Either you need to remember this relation I square equal to minus 1 or remember the value of I equal to root of minus 1. We can do a problem based on this. Find the value of root of minus 25 plus 3 root minus 4 plus 2 root minus 9. Okay, we can simplify this. Remember this value I equal to root of minus 1. So I am going to make a simplification here. This root of 25 can be, minus root of 25 can be written as root of, this can be written as 25 into minus 1. Am I right? Plus, this can be written as 3 into root of 4 into minus 1. 4 into minus 1 is minus 4. Plus 2 into root of 9 into minus 1 is minus 9. Now you know that root of 25 is 5. This root of minus 1 has any value as per our real number system. Plus 3 into 2 into root of minus 1 plus 2 into root of 9 is 3 into root of minus 1. As root of minus 1 has any value in the real number system. But you know that root of minus 1 equal to I. Replace all root of minus 1 with I. So becomes 5I plus 6I plus 3 into 2, 6. Again root of minus 1 is I. The reason is that root of minus 1 can be replaced with the iota I. You can add up all these imaginary numbers. 5 plus 6, 11. 11 plus 6 is 17. I is the answer. You can see what about the positive integral powers of I. Positive integral. Integral means integer. Integer powers of the iota I. We have the only result we have is root of minus 1 equal to I. Root of minus 1 equal to I squaring you get, which implies I square equal to minus 1. This is the basic result for to find the powers of I. I square equal to minus 1 is the basic result. Now, I am going to find the powers of I. What about I raised to 0? We know that any quantity raised to 0 is 1. What about I raised to 1? I raised to 1 equals, I raised to 1 means I. What is the value of I? Root of minus 1. Now I square. I square equal to, I square non-4 minus 1. What about I cube? I cube can be written as I square into I. The value of I square is minus 1. Minus 1 into I equals minus I. What about I raised to 4? I raised to 4 can be written as I square into I square. I square is minus 1 into minus 1 equals plus 1. So I raised to 4 is plus 1. In this way proceeding, can you say what about I raised to 15? I raised to 15 equals, we can write as I raised to 14 into I. Why? Because I raised to 14 can be written as I square the whole raised to 7 into I. What is the reason? A raised to m, the whole raised to n can be written as a raised to m into n. The powers we can multiply together. So, I square the whole raised to 7 means I raised to 2 into 7 equals I raised to 14. But the value of I square can be replaced with a minus 1. So, minus 1 the whole raised to 7 into I. Negative number the whole raised to an odd number is negative into I. So, what is the answer? Minus I. Therefore, what we can say? I raised to 15 equals minus I. Now, I am going to show you what about the negative power of 5. Consider an example as I raised to minus 15. We know that if a negative number or number having negative power, you can make it as positive power by bringing it to the denominator. So, I raised to minus 15 can be written as 1 by I raised to plus 15. The reason is that a raised to minus m can be written as 1 by a raised to plus m. Rules of exponents. Now, I raised to 15 already known for you as minus I. I am going to substitute the value here 1 by. During exam time, you need to find the value of I raised to 15 like this. I raised to 15 is minus I. Now, try to remember an important step. If a minus or if an I is in the denominator, the next step is that 1 by I, if the I is in the denominator, you need to multiply the numerator and the denominator with the same I. Why? Because I divided by I actually is equal to 1. So, it won't alter the value of the expression. So, this can be written as 1 by minus I multiply the numerator and denominator with I. Now, your numerator equals 1 into I is I by your denominator is minus I into I, that is minus I square. Multiply the numerator and denominator with I, you get minus I into I equals minus I square. But you know that this numerator is I itself by minus, keep the minus there. What is I square? I square is minus 1. Now, which is equal to I divided by minus of minus 1 is plus 1. So, the answer is I. So, I raised to 15, I raised to minus 15 equals I. I hope you understand how to do that. When comes with an I in the denominator, multiply the numerator and denominator with the same I. Do some problems. Question 1. find the value of first question, I raised to 37. Second question, I raised to minus 30. First question, you know how to write I raised to 37. I raised to 37 can be written as I raised to 36 into I. I raised to 36 can be written as I square the whole raised to 18 into I. We know that I square equals minus 1. So, minus 1 the whole raised to 18 into I, which is minus 1 the whole raised to an even number is plus 1. 1 into I equals I is the answer. Come with the second question. I raised to minus 30. Negative integral power can take it as positive by bringing it to the denominator. So, I raised to plus 30. Now, I raised to 30 can be written as 1 by I square the whole raised to 15. You need to express each power in terms of I square. I square the whole raised to 15 equals 1 by, again, I square is minus 1. Minus 1 the whole raised to 15 equals 1 by. Negative number the whole raised to odd power is negative. So, the answer is minus 1. Another question. Find the value of I raised to 19 plus 1 by I raised to 25 the whole raised to 2. Don't expand it using a plus b the whole square at first. Do the simplification maximum and then can expand. Solution. I raised to 19 plus 1 by I raised to 25 the whole square, which can be expressed as I raised to 19 can be expressed as I raised to 18 into I plus 1 raised to 25 is 1 by what is I raised to 25? I raised to 25 can be written as I raised to 24 into I. Now the whole raised to 2, which is equal to I raised to 18 can be written as I square the whole raised to 9 into I plus 1 by I raised to 24 can be written as I raised to 2 the whole raised to 12 into I the whole raised to 2 equals, again, I square is minus 1 the whole raised to 9 into I plus 1 by I square is minus 1 the whole raised to 12 into I by, the whole raised to 2 equals minus 1 the whole raised to an odd number is minus 1 into I plus 1 by minus 1 the whole raised to 12 is plus 1 into I the whole raised to 2, which is equal to minus 1 into I is minus I plus 1 by what is 1 into I? 1 into I is I the whole square. Now I am going to do this simplification. Minus I plus 1 by I the whole square can be written as taking LCM as I upon minus I into I minus I square plus 1 the whole raised to 2. Again, minus I square is minus 1. This is the minus in the formula. Then here I square is minus 1 plus 1 divided by I the whole square, which implies minus of minus 1 is plus 1. 1 plus 1 by I the whole square, which implies 2 by I the whole square equals 2 square is 4 by I square equals 4 by I square is minus 1. The answer is minus 4. Do the simplification very carefully. Now we are going to study about equality of two complex numbers. Equality of two complex numbers. Two complex numbers, suppose that they are equal. Two complex numbers, let them be a plus ib and c plus id are equal. Suppose that they are equal. Then it means that a plus ib equals c plus id. They are equal. From this, you need to remember a must be equal to c. That is, their real parts must be equal, and the same way their imaginary parts must be separately equal. So, b equal to d. So, two complex numbers are said to be equal if their real and imaginary parts are separately equal. Real and imaginary parts are separately equal. Then only we can say that they are equal. The complex number which is both real and imaginary is 0. 0 can be written as 0 plus I 0. So 0 can be think as a real part if you consider I into 0 equal to 0. And if you consider this 0, you can say it as purely imaginary. So the complex number which is both real as well as imaginary is 0. 0 is a complex number. From this unit, note one more point. 0 is a complex number which can be written as 0 plus I0. Based on the equality of complex numbers, we can do a problem. The question is, find the values of x and y. Find the values of x and y if the condition given is that 4x plus I into 3x minus y equals 3 minus 6i. You are given with the equality of two complex numbers. You need to find the values of x and y. Since they are equal, what you can say? Since 4x plus I into 3x minus y equal to 3 minus 6i. Two complex numbers are equal. Therefore, their real parts. What are the real parts of these two complex numbers? In the first complex number, the real part is 4x equal to, on the right side, the real part is 3. And equate the imaginary parts also. Imaginary part is the one which comes along with I. Here the imaginary part is 3x minus y, that must be equal to. Here the imaginary part is minus 6. If a minus is there, you need to take that. Now you need to find the values of x and y from these two. So two complex numbers are equal if their real and imaginary parts are separately equal, which implies x equals 3 by 4 and here 3x minus y equal minus 6. Here I am going to substitute the value of x as 3 by 4 minus y equal to minus 6. Reason, using the value for x as 3 by 4. First you got the value for x as 3 by 4, substitute here. Now, which implies 3 into 3 is 9. 9 by 4 minus y equal to minus 6. Which implies I am going to take the minus y to the right side and make it as plus y. 9 by 4 on the left side, minus 6 comes to left side, becomes plus 6. Which implies 4 LCM, 4 upon 9 plus 6 4s are 24 equals y. Therefore, we can say what is the value of y? Therefore, 9 plus 24 is 33 by 4 equals y. Thus, you got the values of x. Therefore, x equals 3 by 4 and y equals 33 by 4. Now we are going to study about algebra of complex numbers. You know that in the case of real numbers, algebra means addition, subtraction, multiplication and division in the case of real numbers. The same will be in the case of the system of complex numbers too. We are going to study each operation separately. Let Z1 equals A1 plus IB1 and Z2 equals A2 plus IB2. Real part of Z1 equal to A1. Imaginary part of Z1 equals B1. Real part of Z2 equals A2 and imaginary part of Z2 equals B2. Now I am going to add up these two. What about Z1 plus Z2? Z1 plus Z2 equals A1 plus IB1, that you need to add with the A2 plus IB2. You need to add the real part separately, that is A1 plus A2 in one bracket, real part separately, plus IB1 plus IB2. So that I you can take common outside, IB1 plus IB2 can be written as I into B1 plus B2. Clearly this is also a complex number. Here one more result. What about a real part of Z1 plus Z2? Equals, what is the real part of Z1 plus Z2? A1 plus A2. What is A1? A1 is the real part of Z1. A1 is the real part of Z1 and A2 is the real part of Z2. From this you identify one more result, a real part of Z1 plus Z2. That is, if two complex numbers are adding, their real part of Z1 plus Z2 equals real Z1 plus real Z2. This is a very important property. When adding two complex numbers, their real part, sum of the real parts must be equal to adding the real part separately. In the same way, what about imaginary part of Z1 plus Z2? In this case, imaginary part is B1 plus B2. B1 plus B2. What is B1? B1 is the imaginary part of Z1 plus B2 is the imaginary part of Z2. From this one more result you can see imaginary part of Z1 plus Z2 equal to imaginary Z1 plus imaginary part of Z2. So remember these two results. Real part of Z1 plus Z2 equals real Z1 plus real Z2 and imaginary part of Z1 plus Z2 equals imaginary Z1 plus imaginary Z2. This is regarding addition of complex numbers. Now we are going to study about some properties of complex numbers. Properties of addition. The first is the closure law. In the case of real numbers, you know that the closure law states that if we add two real numbers, we get another real number. In the same way, adding two complex numbers results in another complex number. The second property is the commutative property. Just like the commutative property of real numbers, the second law is the commutative law. What the commutative law states, A plus B equal to B plus A. In the same way, let Z1 equals A1 plus IB1 be one complex number and Z2 equals A2 plus IB2 another complex number. I am going to add Z1 plus Z2 equals A1 plus IB1, that you need to add with the A2 plus IB2. You know how to add two complex numbers. Add the real part separately, that is A1 plus A2 plus IB1 plus IB2. I taking common outside B1 plus B2. Now I am going to add Z2 plus Z1. Z2 plus Z1 is Z2 you need to add first A2 plus IB2 that you need to add with the a1 plus ib1. Here also a2 plus a1 in one bracket, adding the results, plus ib2 plus ib1 can be written as I into b2 plus b1. Now, looking at this, you can see that, look at the right side. Looking at this, you can see that a1 plus a2 is the same as a2 plus a1 because a1 and a2 are real numbers. And same way, b1 plus b2 is the same as b2 plus b1. So, what you want to write here? a1 plus a2 is the same as a2 plus a1. And b1 plus b2 is the same as b2 plus b1. Therefore, the commutative law holds z1 plus z2 equals z2 plus z1. Come with the third law. What is the third law in the case of real numbers? The associative law. The same here also, associative law. If z1, z2, z3 are three complex numbers, then z1 plus z2 plus z3 in one bracket is the same as z1 plus z2 in one bracket plus z3. I don't wish to prove this. If you want, you can prove just like by taking three numbers as z1 as a1 plus ib1, z2 a2 plus ib2, one more real number, complex number, z3 as a3 plus ib3. And if you want, you can check. Now I need to study the proof and then come with the fourth property. What is the fourth property in the case of real numbers? Existence of additive identity. Existence of additive identity. Additive identity. In the case of real numbers, we know that if 5 is a real number, what is the additive identity? Additive identity is the number which gives the same number. That is, the operation with the 0 gives the same number, which is the same as 0 plus 5. So, additive identity means that 0 is the additive identity in the case of real numbers. In the same way, if z equals a complex number a plus ib, then there exists a complex number, there exists a complex number, you know that 0 equals 0 plus I0. Real and imaginary parts are 0, such that z plus 0 is the same as 0 plus z. Both will give the number z. So, as in the case of real numbers, the four properties holds. That is closure, commutative, associative, and existence of additive identity. You can see the fifth property. What is the fifth property in the case of real numbers? Existence of additive inverse. Existence of additive inverse. What do you mean with additive inverse? Additive inverse means, in the case of real numbers, additive inverse means if you take a number 5, you need to add up with that another number to give the additive identity 0. So 5 when adding with a minus 5 gives the number or gives the additive identity 0. So minus 5 is called the additive identity in the case of real numbers. In the same way, for complex numbers also there exists an additive inverse. For every complex number, I am going to take a complex number z equal to a plus ib. There exists a complex number, that also a complex number, there exists a complex number minus z equals minus a minus ib. Both are negative. Minus a minus ib. Why? when adding z plus minus z, we need to get the additive identity 0. Minus z equals minus a minus ib, such that z plus minus z, when adding you get a plus ib plus minus a plus minus ib, you get 0, which is the same as minus z plus z. Here 0 is the, here minus z is the additive inverse of z. Example, if z equals 4 plus 3i, then its additive inverse is minus 4 minus 3i. Minus z equals minus 4 minus 3i. Why? We can check z plus minus z equals 4 plus 3i, that you need to add with the minus 4 minus 3i. So that adding the real parts, you get 4 plus minus 4 in one bracket plus 3i plus minus 3i in the other bracket. If you want, you can take the I common outside. Here 0 plus I 0, which is the additive identity. So for every real number, there is a additive inverse. In the same way, for every complex number, there exists an additive inverse. Now we are going to study the next property. So in the case of addition, 5 laws are there with the closure law, commutative law, associative law, existence of additive identity, and existence of additive inverse. Now we are going to study about the second operation, that is subtraction of two complex numbers. Subtraction of complex numbers. Just like the subtraction of real numbers, complex numbers also can be subtracted. Suppose that I am going to take two complex numbers. If z1 equals a1 plus I b1 and z2 equals a2 plus I b2, then z1 minus z2, these are two complex numbers, z1 minus I1, z2 equals a1 plus I b1 minus of a2 plus I b2. How to subtract these two? Subtracting the real part separately, a1 minus a2 in one bracket plus ib1 minus ib2, I you can take common outside, b1 minus b2. Look at this one. This is also a complex number having a real part and an imaginary part. Operation. The third operation, multiplication of complex numbers. Multiplication of complex numbers. Just like the multiplication of real numbers, complex numbers also can be multiplied together. I am going to take two complex numbers. If z1 equals a1 plus I b1 and z2 equals a2 plus I b2, be two complex numbers, then the product, what is the product of those two complex numbers? The product z1 into z2 equals a1 plus I b1 into a2 plus I b2. Okay, just like the multiplication of real numbers, we can multiply a1 a2, the first one a1 a2 plus a1 into ib2, a1 into ib2, that I am going to write it first, a1 into ib2. So I can write it as I a1 b2 plus the next is I b1 a2, I b1 a2, b1 a2 plus the last one is I into I, that is I square. Am I right? I into I is I square, then b1 b2, b1 b2. Just like the multiplication of real numbers equals a1 a2 plus I a1 b2 plus I b1 a2, I square is minus 1. So minus b1 b2. The reason is I square equals minus 1. Now I am going to combine the like terms a1 a2 minus b1 b2. Numbers having any I or imaginary along with it are called real numbers. So a1 a2 minus b1 b2 is the real part, plus from these two terms I am going to take an I common outside. So a1 b2 plus b1 a2. You can see that it is also a complex number having this one as the real part and this one as the imaginary part. Then, just like the properties of addition, multiplication also holds some properties. Properties of multiplication. Properties of multiplication of complex numbers. What is the first property in the case of multiplication of real numbers? That is the closure law itself. The first one is closure law. Closure law. What about closure law? If two complex numbers you multiply, then if Z1 and Z2 are two complex numbers, then Z1 into Z2, you can see that Z1 into Z2 is also a complex number. That is the closure law. What is the second property in the case of multiplication of real numbers? The commutative law. Commutative law. What the commutative law states? If Z1 and Z2 are two complex numbers, then commutative law states that what the commutative law states? Z1 into Z2. Commutative law of multiplication. So Z1 into Z2 must be the same as Z2 into Z1. This is commutative law. Now, the third one, the associative law. Associative law. Associative law states that for any three complex numbers, I am going to take three complex numbers Z1, Z2 and Z3. I am going to take three complex numbers. The commutative law states that Z1 into Z2 into Z3 in one bracket is the same as Z1 into Z2 in one bracket into Z3. Property in the case of multiplication of complex numbers, which is the existence of multiplicative identity. Existence of multiplicative identity. What is the multiplicative identity in the case of real numbers? For to get the multiplicative identity, you know that if 5 is a number, you need to multiply with something to get the identity element or to get the same element 5. Here 1 is the number you need to multiply to get the same number 5. But in the case of addition, for to get the same number, you need to add with the identity 0. So 1 and 0 are the multiplicative and additive identity in the case of real numbers. In the same way, additive identity in the case of complex number is 0, already studied. But multiplicative identity we can see just like the real numbers, just like the real numbers are 1 can be written as 1 plus I0, the imaginary part of 0 is the multiplicative identity. Is the multiplicative identity for complex numbers. Multiplicative identity of complex numbers. So, remember, as per the multiplicative identity for real numbers, 1 which is 1 plus I0 is the multiplicative identity for complex numbers. Now come to the fifth property. Existence of multiplicative inverse. Existence of multiplicative inverse. Multiplicative TIV. Multiplicative inverse. You know that for a real number 5, to get the multiplicative identity 1, what you need to multiply? You need to multiply with the 1 by 5. Here, 1 by 5 can be called as the multiplicative inverse of 5 in the case of real numbers. Similarly, in the case of complex numbers, for every complex number Z, for every complex number Z, there exists a complex number, there exists a complex number 1 by Z, 1 by Z, such that the peculiarity is that Z, when multiplying with 1 by Z, you get the multiplicative identity 1. So here 1 by Z is called 1 by Z is called the multiplicative inverse. Is called the multiplicative inverse. So these are the properties for multiplication: closure law, commutative law, associative law, existence of multiplicative identity, and existence of multiplicative inverse. Now, one more additional property you need to study, as in the case of real numbers, the distributive law. Distributive law. What the distributive law states? If Z1, Z2 and Z3 are 3 complex numbers, if you consider 3 complex numbers, then the distributive law states that Z1 into Z2 plus Z3 equals Z1 into Z2 plus Z1 into Z3. This we can call as the left distributive law. The left distributive law. But if you write like this, Z1 plus Z2 into Z3 equals, that is the right distributive law, Z1 into Z3 plus Z2 into Z3. This is the right distributive law. Right distributive law. It is the conjugate of a complex number. Conjugate. The conjugate of a complex number. Listen to this. The conjugate of a complex number, the conjugate of a complex number Z, of a complex number Z, is obtained by changing the sign of, by changing the sign of the imaginary part. The imaginary part. The conjugate of a complex number is obtained by changing the sign of the imaginary part only. Changing the sign of the imaginary part only. The conjugate of a complex number Z is usually denoted as Z bar. Read it as Z bar. So, if Z equals 3 plus 2i, then its conjugate Z bar equals, change the sign of the imaginary part alone, that is 3 minus 2i. But if z equals minus 4 minus 3i, then its conjugate z bar equals, change the sign of the imaginary part alone, minus 4 as if it is imaginary part sign gets changed as plus i3 or 3i, both are same. See the last property that we studied, addition, subtraction, multiplication, the conjugate, and now we are going to study about division of complex numbers. Division of complex numbers. That seems to be a very important section, division of complex numbers. The conjugate as well as division, both are important. For to divide two complex numbers, if z1 and z2 are two complex numbers, then z1 by z2 is also a complex number. Is also a complex number. That is the property holding here. Complex number. Let us see an example for division of complex numbers. Example. Let z1 equals 6 plus 3i and z2 equals 2 minus i. I am going to find z1 by z2. z1 by z2 I am going to find. z1 by z2 means 6 plus 3i that you need to divide with a 2 minus i. Remember the property here. The first step is multiplying the numerator and denominator by the conjugate of 2 minus i. The conjugate of the denominator 2 minus i. Always remember, this is the step which we need to proceed for dividing. That is why I teach conjugate of complex numbers at first. So we are going to divide. So z1 by z2 equals 6 plus 3i divided by 2 minus i is there with. You need to multiply the numerator and denominator with the conjugate of 2 minus i. That is 2 plus i on the numerator and denominator. Now we can proceed. Now how it comes? 6 plus 3i into 2 plus i divided by 2 minus i into 2 plus i. We are going to multiply. You know how to do the multiplication of two complex numbers. 6 into 2, 12, plus 6 into I, 6i, plus 3i into 2, 6i, plus 3i into I, 3i square, divided by. In the denominator, you can apply the property a minus b into a plus b. A square minus b square is I square. Okay, we can proceed further, which is equal to, I am going to combine the like terms, 12. Here if you want, you can write one more step, 12 plus 6i plus 6i is 12i. 3i square is minus 1. So 3 into minus 1 is minus 3. The whole divided by 2 square is 4 minus I square is minus 1. Again, 12 minus 3 is 9 plus 12 I divided by 4 minus 1, 4 plus 1 which is 5. So this is the answer of z1 by z2. If you want, you can write like this also, which is equal to 9 by 5 plus I 12 by 5. Again a complex number having a real part as 9 by 5 and imaginary part as 12 by 5. So this is the procedure for to find the division of two complex numbers. The identities related to complex numbers. Identities related to complex numbers. First identity, just like the real numbers, z1 plus z2 the whole square. You can apply the identity as z1 square plus z2 z1 into z2 plus z2 square, just like a plus b the whole square. Second identity is z1 minus z2 the whole square equals z1 square minus 2 z1 z2 plus z2 square, a minus b the whole square. The third one, z1 plus z2 the whole cube equals, what is a plus b the whole cube? A cube plus 3a square into b plus 3a into b square plus last one is b cube. The same is the case of z1, fourth one, z1 minus z2 the whole cube, that is a minus b the whole cube. A minus b the whole cube is a cube minus 3a square into b plus 3ab square minus b cube. And come with the last one, z1 square minus z2 square. A square minus b square can be written as a plus b in one bracket into a minus b in the other bracket.